So this is a joint work with Lunjia Hu, Tianhong Li, and Liwei Wang. Wu, Li, and I are all Yale class undergraduate in the third year. In this work, we mainly discussed about a recursive teaching dimension. It's a complexity measure in the recursive teaching model, just as the VC dimension is a complexity measure in PAC learning. So the difference between VC dimension and RT and the recursive teaching dimension is as follows. When we talk about the VC dimension, where we are in the PAC learning scenario, where we do passive learning and the data are drawn independently at random. But with the help of teacher, we can choose the data selected by the teacher. So these two complexity measures are in very different learning situations, but interestingly, they have a very close relationship that the recursive teaching dimension is bounded by VC dimension. Before we go into technical details, we first quickly go through some basic definitions in learning theory. First, we have concepts, and since here we always talk about finite concept classes, so we can assume without loss of generality that our ground set is also finite, which is 1 through n, and concepts are binary functions that give labels to these examples in the ground set. And for every subset of the ground set, we consider the projectional pattern on this subset. So, for example, we can for some subsets we call them shattered sets. If the concept class covers all 2 to the size of x possible patterns on this subset. And for some subset we call it a teaching set for a certain concept, which means that we can distinguish the concept only by looking at the labels on this subset. So, and based on this notation, we can define VC dimension, which is known as the largest size of the shattered set, and also the teaching dimension, which is the smallest size of the teaching set for every particular concept. And here, TD mean, which is also called the best case teaching dimension, is defined as the minimum teaching dimension for all concepts. The definition of recursive teaching dimension is based on the recursive teaching hierarchy, which is a sequence of concept classes defined in a way that every concept class is chosen by deleting all the concepts in the previous concept class that has the minimum teaching dimension. So after we get this hierarchy, we can define recursive teaching dimension to be the maximum one of the maximum teaching, the maximum TD mean of this sequence of concept classes. So in year 2015, Simon and Zils proposed an open problem conjecturing that the recursive teaching dimension of a concept class is bounded by its VC dimension linearly. So here we always discuss finite concept classes, since for general infinite concept classes, this result is not true, and actually the recursive dimension can be infinity. So in 2015, Moran et al. Proved this result. This is before the open problem was proposed. And then in year 2016, Chen et al. Improved the result, and a result that is independent of the size of the concept class. So this is an exponential upper bound. And in this work, we proved a quadratic upper bound. So the main technique we use is to generalize a little bit the definition of VC dimension. So we define XY classes as the concept classes having at most Y different patterns. If we only look at labels on X, X is chosen as subset of size at most small x. So for example, just as an example, the VC dimension D means that the concept class is D plus 1, 2 to the D plus 1 minus 1 class, because the largest shattered set has size D. So every subset of size D plus 1 is not shattered. So it has to be 2 to the D plus 1 minus 1. So there's a minus 1 there. So more generally, so we have the Sawyer's lemma, which states that the VC dimension D means that they are EX over D to the D classes for all x greater than D. And so based on these notations, we define f of xy as the largest TD mean of all finite xy classes. So this f function is used in our proof. So now let's start the proof. So we start with the f function. So we first construct a recursive formula for f function, and then based on this recursive formula, we choose a proper value for y and z, and then we recurse on x. We get a quadratic bound for f of x and alpha to the x. Then we apply Sawyer's lemma, and this is then naturally we get this quadratic bound for TD mean of concept classes, and then by a standard reduction, which is widely used in previous research, then we get the quadratic bound for recursive teaching dimension. So here now we get a quadratic bound. So but the conjecture is a linear one. So now let's discuss how far are we from the linear result. So here if we look at the recursion, we can see that if we choose these values, so in each recursive step, we have a linear adding term here, and then and then by solving the recursion, we get a quadratic form. So if we want to strengthen this method to make it the linear bound, it's kind of hard, since we need a constant addition here, which doesn't seem easy. So it seems that actually we tried a lot to improve this bound, but it seems hard that this recursive formula, by improving the recursive formula, we can get a better bound, not even nearly, just better than quadratic. It's not very easy. So perhaps new insights are needed for improving these results. So we have some. So if we want to look more into this problem, there are some interesting problems that we can look at. So the first is to find specific values for f function. So actually, the first result for this whole research history is by Coleman in 1999, who proved that f23 equals to 1, which means that all the concept classes with VC dimension 1 has to have a recursive teaching dimension at most 1. So these are specific cases, and actually we generalize all these specific cases to get our general result. And the other is to try to study the landscape of that function. So thank you.